Hi guys, you're welcome to God Academy. In this lesson, I'll be taking you through mathematical induction, specifically the type 1. As we've gone through in the previous lessons on integers, natural numbers, rational numbers, and the different number categories under the number systems, we proceed with one powerful properties of positive integers called mathematical induction. So this is a property which helps us to determine that a particular mathematical statement is true for every positive integer. So I'm going to use the type 1 to explain mathematical induction. So the problem here is prove that 1 plus 2 plus dot 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 plus n is equal to n, multiplying n plus 1 is equal to 2. Do you understand this? What this statement is trying to say is that if you have a series of positive integers, 1 plus, so this is a series, that is a sum of sequence. Remember that natural numbers are written in sequence, so 1, comma 2, comma 3, comma 4. So when I add each term to the other term or to the next term, I end up getting what you call a series, okay? So what the problem is trying to say is, if I have a series of positive integers summing up to any nth term, any number of terms that you are summing up to, it always gives us that number of terms which you are using times the number of terms plus 1 over 2. How sure that this statement is true for every positive integer? That is what mathematical induction seeks to prove. Assuming that I have 1 plus 2, I'm adding the first two terms of the positive integer. What do I get? I get 3. When I come here, I use n, which is 2 integers, that is 1 and 2. So I'm going to write 2 multiplying 2 plus 1 all over 2. What do I get? I get 2 times 3 all over 2. This gives me what? This cancels this 3. Meaning it's true. So when I added the first two terms, it was 3. On the right hand side, this formula here proved that it's 3, and then I can say that their statement is true. But how sure am I that this statement may not be true when I'm adding maybe 100, 200, 2000, 5000? That is why mathematical induction seeks to solve this problem or seeks to close this gap. Now let's solve this systematically so that you understand the principles of mathematical induction. So the first step in mathematical induction is what we call the base case. Base case. Exactly what we just did. The base case states that if your statement is true, then it should be true for the base situation, the basic situation you can ever get. So now, n stands for the number of terms you are trying to add. Now, the base case, mostly you can have n equals 1. You can test for the basic scenario. So let's see. So proving for n is equal to 1, what do you have? On the left hand side, I'll have LHS to be equal to 1 because when n is 1, it's only the first term which you are talking about. The right hand side gives me 1, 1 plus 1 all over 2. Why? Because n is 1. I'm looking at only one term when n is 1, okay? So this gives me 1 multiplying 2 all over 2, and this gives me 1. You can see the left hand side and the right hand side are equal. So I'll say that my base case is true. What if we can confirm more base cases? Now let's choose when n is equal to 3. When n is 3, we can test for 1 plus 2 plus 3. That is summing the first 3 terms, right? On the left hand side, okay? That gives me 3 plus 3, that is 6. On the right hand side, what do I get? I get my n, which I chose 3. I'll have 3 multiplying 3 plus 1 all over 2. This gives me 3 multiplying 4 all over 2. And that is going to be 3 times 4 is 12 over 2, which is 6. Hence, the left hand side and the right hand side being the same, hence the base case is true. So now we've confirmed using the basic number of terms to prove that indeed this statement here is true. Now, here comes mathematical induction second step. Number 2 is what we call induction hypothesis. Induction hypothesis. So in induction hypothesis, we assume that our statement is true for n equals k, which is an unknown number. So assuming. So the second step is an assumption, right? So assuming the statement is true for n is equal to k, right? So here we are going to assume that the statement here is true for n equals k. Why? Because since we have been testing for 1, we've tested for 3, we can't be testing for 5, 6, 7. So let's assume that we are testing for n equals k, where k can be any number of terms, right? And the induction hypothesis says that we assume that when n equals k, the statement is true. Let's assume that that k at the kth term, the statement still holds, okay? Therefore, our statement then becomes 1 plus 2 plus dot 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 plus what? K. Because now the n here is k at the kth term, right? This should be equal to, wherever I see n on my right hand side, I put k. K multiplying k plus 1 all over 2. Therefore, I'll say that this statement here is true, right? This is true. This is what we call the induction hypothesis. So it's a tentative guess that at n equals k, our statement is true. Now let's come to the inductive step. That is the number 3. This is what we call the inductive step, okay? Inductive step. At the inductive step, what we do is we prove for the next number after the unknown. So prove for n is equal to k plus 1. So this is where we are actually doing the mathematical induction, because we want to know that if indeed our statement is true for any arbitrary number k, then if it is true, then the next number k plus 1 should also work. Once that works, it means that it's going to work for every positive integer, because we don't know k. K can be any number. So if k is true and it's working for k plus 1, then it means that it will work for everything. So let's prove the inductive step. At the inductive step, you go back to the statement. So now you are looking for n, where is k plus 1? That is the next term after k, right? So our statement then becomes 1 plus 2 plus dot 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 plus k, then plus k plus 1, because we are looking for the k plus 1's term, okay? Should be equal to, now on my right hand side is just a placeholder, okay? The right hand side is just n. So wherever I see n, I put whatever terms I'm using. So now I'm using the k plus 1 term. So using the k plus 1 term, wherever I see k, I put k plus 1 multiplying k plus 1 plus 1. So it's like wherever I see k, I put k plus 1. Check here. Okay. So at this point, you can clearly see that n is now k plus 1. So I'll have k plus 1 for this outside here. This k now become k plus 1 here. This k inside become k plus 1 plus 1 all over 2. As simple as that. So all over 2. Now, in my simplification, you realize that 1 plus 2 plus dot 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 plus k is my inductive hypothesis. So what I have here is the same thing I have here, right? And you realize that we accepted that this statement is true and it amounts to this right hand side. So I can replace this whole hypothesis with what I assume to be true. With that, what I get is I'll have this removed and I'll bring my k multiplying k plus 1 all over 2 plus on my here k plus 1 is equal to my right hand side k plus 1. This now become k plus 1 plus 1, so k plus 2. all over 2. So let's simplify. So here I'll have cross multiply algebraic expression. So k plus 1. You cross multiply, you have plus 2k plus 2, right? All over 2. This should be equal to, here you multiply k squared plus 2k, then 1 times k plus 2, right? All over 2. At this point, you do same. So k squared plus k plus 2k plus 2 all over 2 is equal to, I simplify, I have my k squared plus 3k plus 2 all over 2. Here to become k squared plus 3k plus 2 all over. So I can see that my left hand side and my right hand side are equal. Therefore, I will say that my statement from the question, I'll clearly say that my statement 1 plus 2 plus dot 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 plus n to this is true for all positive integers. That is simply mathematical induction. So therefore, our statement is true for all positive integers. And that is all for mathematical induction. It's simply showing that your left hand side of a statement is equal to the right hand side. Thank you for being with me in this video. If this is the first time being on this channel, kindly subscribe and make sure you follow the entire algebra course.